Okay, so now we are in section 16.4, and we're going to talk about one of the major theorems of vector calculus, which is Green's theorem. So to start with, we're going to have to introduce some more terminology. So we're going to let C be a simple closed curve, and it's going to be enclosing some plane region that we're going to call D. If the vector function r of t, where t goes from a to b, is the function that gives us this plane curve C, and if as t goes through that parameter interval, if C is traversed exactly once, we say that C has positive orientation if the orientation given by this curve keeps the region D on the left as the point moves along the curve. You can kind of think of that as like a counterclockwise orientation. So if you can see this region right here, this region has positive orientation, and you know that by, or sorry, the curve regions don't have orientation. The curve, boundary curve, has positive orientation because if you follow the arrows giving me this orientation, D will be on the left side of this point as it moves forward. You can kind of think of yourself as walking along this curve in that direction, and if you look to your left at any given time, you'll see the region D. Negative orientation is the opposite. You can think of that as like a clockwise orientation. Green's theorem, in the hypotheses of Green's theorem, we're assuming that the curve that's bounding this region that we want to consider for integration is always positively oriented. In addition to that, any plane region is called simple if it's both a type 1 and type 2 region, which by type 1 and type 2, I'm talking about the type 1 and type 2 regions back in chapter 15 that we introduced early on, where we talked about evaluating double integrals over those types of regions. So if a plane region can be expressed as either type, we call that simple. All right, let's go ahead and state Green's theorem. So for Green's theorem, we're going to have a positively oriented, piecewise smooth, simple closed curve called C. I know that's a mouthful, but basically it's describing curves of this type. And D is going to be the region that's enclosed by that region, by that curve C. Okay, now what we're going to do is compare a line integral around this boundary curve, which I can show you up here. We're going to compare a line integral around this boundary curve to a double integral over the region that it encloses. And Green's theorem states that these two specific types of line integrals will be equal to each other. So if the these two types of integrals, if the line integral is has as its integrand p dx plus q dy. Remember, p and q in this case are going to be functions of two variables. That Green's theorem says that we can evaluate this line integral by converting it to a double integral whose integrand is the partial derivative of q, this q, with respect to x, minus the partial derivative of p, this p, with respect to y, dA. Okay, so notice the integrands don't look identical, but they shouldn't, because we don't integrate the same types of functions necessarily here as we do here. So, however, the p and the q here are related in the sense that the partial derivatives of these functions show up over here. Okay, so we are going to go ahead and prove Green's theorem, but we don't have the tools to prove the most general case, which is what's stated here. We can only prove right now, or we're only going to prove Green's theorem in the case where the region D is a simple region, meaning it can be, like we said, represented as a type 1 or a type 2 region. So I want to make sure that's made clear. This proof is for a specific special case of Green's theorem when that region D is simple, but Green's theorem does apply to more general regions. In fact, after we prove this and we look at an example or two, we're going to extend Green's theorem to a wider range of regions as well. So first of all, Remember that this integral right here can be split into a sum of two line integrals. The line integral along c of p dx, and then another of q dy. This notation is just shorthand for adding those two. Also, if we look at this double integral, because there's a difference here, I could also split this up into two double integrals. One where the double integral has as its integrand the partial of q with respect to x, and the other one negative partial of p with respect to y. So it turns out that the best way to approach this, if we want to prove it, is to split each of these into two parts and prove that one of the parts over here equals one of the parts over here, and the other part over here on the left equals the other part on the right. Namely, the line integral along c of p dx is going to be equal to this part of the double integral in Green's theorem. It's going to be equal to negative the double integral of over d of the partial of p with respect to y dA. And then similar down here, I'm going to prove that this part of the line integral up here is equal to this part of the double integral here. If I can prove these, then adding these two equations will give me Green's theorem. This plus this is equal to this. This plus this is equal to this. Okay? So we're going to focus first on this, this equation right here, equation 2. The way we're going to do this is use the assumption that we're dealing with a simple region, which means that we can represent our region D as either a type 1 or a type 2. And I'm going to represent it as a type 1 region here. So remember, that means that x is in a constant interval and y is bounded by functions of x. That's what makes this a type 1 region. On the next page, I'll show you an image of what it is that we're looking at here. Okay. We're also making the assumption, because this is the case for type 1 regions, that g1 and g2 are continuous functions. And so if I wanted to evaluate the double integral here, the double integral of the partial derivative of p with respect to y, let's think about what that would look like. I have to convert this into an iterated integral using the way that I represented d here, which would look like this. Notice my limits of integration on the inside are g1 to g2. And also, because these represent values for y, I'm integrating with respect to y first. Now, this is a double integral, or sorry, this is a multivariable function, a function of x and y here. But it's specifically one that was obtained from p by taking a partial derivative with respect to y. And then as our very first step, we're taking a partial integral with respect to y. And so the fundamental theorem of calculus applies here because these two things match. An antiderivative of this function here would just be p if it's an antiderivative with respect to y specifically. So evaluating this first inner integral, the antiderivative I use is p of xy, and that's what we have here. But then because I had limits of integration, it's a definite integral, these have to be put in for y. So the g2 of x becomes the y here, g1 of x becomes the y here, and as we do with definite integrals, we subtract those. Okay? So really all we used here was the fundamental theorem of calculus to represent this double integral in this way. Okay? Now we're going to leave this here for now, and now what we're going to do is, coming back up here to equation 2, we're going to start working on the left-hand side. But in order to do that, we have to take a look at the curve that surrounds this region D, or encloses it. And this is straight out of your book. The whole proof is straight out of your book. I'm just kind of talking you through it. This is one possible representation of that region D. So notice we represented it as a type 1 region, so here's G2 up here, here's G1 down here, and then we have these two other sort of boundaries for D on the left and right side. I'm going to take those 4 curves that make up the boundary and give them names, C1, C2, C3, and C4, as you can see here, okay? All right, so keep that picture in mind. Coming back here, what we want to do is use the fact that C, which represents the union of all 4 of those curves, and break it up into a line integral for each one of those curves. Remember, I can write this as the sum of the 4 line integrals along C1 and then along C2, C3, and C4. and I want to see what happens to those individual pieces. Okay, so that's what's being described down here. Now, remember, because this is a line integral that we're evaluating, if we want to evaluate it directly, we have to have a parametrization for these curves. But these parametrizations are easy to come up with if if a curve has one variable represented as a function of the other. I just make the independent variable my parameter, and then y is g2 of t, if I'm using t as my parameter. So that's going to let me represent this function, my line integral along c1. Here's c1, which is given by the curve g1 of x. I'm going to let x be my parameter, and in this proof they don't change the x into a t, they just let it remain an x. And then y is g1 of x, and the dx will just remain a dx here. So this is how I can convert this first line integral here into a definite integral. Okay. Now, because this thing is positively oriented, you know, it's kind of going counterclockwise as we traverse this curve. Along C1, as we kind of move in the direction of that orientation, we're going from left to right. But in C3, as we move in the direction of that orientation, we're going from right to left. So if that's the case, then negative C3 would reverse that orientation and take me from left to right. And the reason that matters is because if I'm going to be using x as my parameter, then as x increases, x is actually one of the axes here. As x increases, that's always taking me from left to right. So I want to think of what's happening to these curves as x increases, which is why we're going to consider taking C3 in the opposite direction here. So if that's the case, then I can use a similar parametrization as before. C3 can be parametrized by x equals x, which I have here, y equals g2 of x, and, sorry, negative C3, we're parametrizing that way. So if I wanted the line integral along C3, I convert that into a line integral along negative C3, but then I make that line integral negative using that property that we've talked about in the past. And then I look at the parametrization of this. We just parametrized negative C3. It's x equals x, y equals g2 of x, and x ranges from a to b, which is I'm getting from this right here. Okay, so this is going to give me the second of those four line integrals that I need. Now, what happens to C2 and C4? Well, again, if I parametrize with respect to x, notice this is a piece of the line x equals a, and this is a piece of the line x equals b. So these functions are constant with respect to x. So that being the case, if I were to try to compute the line integrals along either of these, I would need dx in my parametrization, but dx will be 0 because x is a constant function. So that means that both of these line integrals are going to come out to be 0. So with that, taking the line integral now of p of xy dx along c, what we did is we said we would break it up into those four pieces, one for each part of this boundary curve that makes up C. Two of these pieces went to 0, which we showed up here. That's this one and this one. And the other two pieces we came up with representations for as definite integrals by parametrizing, which gave us this. Notice if I combine these two into a single definite integral, then what I would have is p of x g1 of x minus p of x g2 of x as my integrand, all with dx. It's the opposite of what I have here. Notice the g2 is coming first here, but that's okay because remember what we evaluated here was the double integral where my integrand was the partial of p with respect to y, and we wanted to show that the line integral we just evaluated is equal to the opposite of that. That would switch the order of these two terms in the integrand. So basically that entire argument shows that the line integral along C of p dx is equal to the negative double integral of the partial of p dy so partial of p with respect to y dA. Okay, it's a lot of work to get through that proof, and notice that was only half of it because again we've only established equation 2 here. Equation 3 also needs to be established so that we can add these two things and get Green's theorem. But the derivation of this part is essentially the same idea. The only difference is that we would represent D as a type 2 region instead and go through similar steps. And that's the reason why for a proof of this type we need D to be a simple region, one that can be represented as both a type 1 and a type 2. Okay? Now with that said, there's some alternate notation that we're going to encounter as we go through some of this work. So I just want to introduce that really quickly. This one shows up here and there, but it's a line integral, and these may look the same to you, but there's a circle right in the middle of each integral sign, and this one has a little arrow pointing down, showing that the orientation of this circle is counterclockwise. Basically, what this is this is showing that the line integral that we're taking is using a curve that's a positively oriented closed curve, simple closed curve. If you left that circle off, in most cases, it's not going to make any difference because the C would have been described somewhere. So you don't need the circle to tell you that it's a closed curve. But this does come up here and there, so it's worth knowing that notation. This notation we will use a little bit later. Sometimes, if you think about it in the statement of Green's theorem, we have two things. We have the boundary curve that we call C, and then we have the region that it encloses, which is called D. In some cases, we want to focus primarily just on D, that region, and rather than come up with a new symbol to represent its boundary curve, we use this little symbol right here. Which this is interpreted as a curve, but just the boundary of the region D here. This is a really common notation in this area in vector calculus, so it's good to know that as well. Okay, I think what we'll do is run through one example of using Green's theorem and then wrap this video up before we move on to areas in the next video. So in this one, what we're doing is we're evaluating a line integral of x squared plus y squared dx plus x squared minus y squared dy, and C is the positively oriented triangle with vertices 0, 0, 2, 1, and 0, 1. You can evaluate this directly, but look at the curve for a moment. Excuse me. So x and y, here's my vertices, 0, 0, 2, 1, so 1, 2, 1, that's 2, 1 right there. And then 0, 0, 1, so the triangle is this one. It's positively oriented, we're just given that information in the problem. So as we traverse this triangle, D should be on our left the entire time. That means it's oriented this way. Now, if I wanted to evaluate this line integral directly, it's not a pretty process because I have to break this line integral into 3 pieces because my boundary curve is made up of 3 independent pieces. And then I have to parametrize these pieces, which isn't terrible, it's not that bad, but when you consider the integrands that we're using, this can end up getting kind of messy and tedious. Green's theorem takes problems like this and makes them go usually much faster. So what we're going to do is change this line integral into a double integral, and that's what Green's theorem allows us to do. The double integral doesn't consider the curve, the double integral considers the region that's bounded by the curve. So first of all, notice that this line for this part of the triangle right here is part of the function y equals 1/2 x. It's a line with a slope of 1/2 passing through the origin. This right here is a piece of the line y equals 1. So I can represent this as a type 1 region where 1/2 x and 1 are my bounds on y. And then x will go from 1 to 2. Also, in Green's theorem, remember, we're taking line integrals of the form p dx plus q dy here. And Green's theorem is going to require me to use partial of q with respect to y minus the partial of p, with respect to x, that one's with respect to x, partial of p with respect to y. Well, what does that look like in this case? If this is q, x squared minus y squared, then the partial of q with respect to x would be 2x. Similarly, the partial of p, this function, x squared plus y squared with respect to y, would be 2y. So this becomes minus 2y. Okay, so that means this line integral can be evaluated as the double integral over d, where my integrand now looks much simpler than it did up here. It's just 2x minus 2y dA. Evaluating this double integral is not that bad. It's a pretty nice type 1 region. Being a type 1 region, we're going to integrate from 0 to 2 for our x, and like we said, our bounds on our y go from 1/2 x up to 1. And again, here's our integrand, 2x minus 2y, dy on the inside, dx on the outside. Okay, this isn't that bad to integrate, like I said, so this is going to become 0 to 2. And we're integrating with respect to y first, so I'm going to get a 2xy right there, minus, this would become y squared from 0 to 2 dx. Oh, no, sorry. Wrong limits of integration. That should be 1/2 x. That's 1 right there. Okay. And then, let's see, what do we end up with for this? So we're going to get the integral from 0 to 2. Plug in my 1 first for y, so that would become 2x minus 1. Minus, plug in 1/2 x for y, and that's going to become x squared. Plug in 1/2 x here, it becomes minus 1/4 x squared dx. Integrate from 0 to 2. Let's see, what do we get? This is going to become 3/4 x squared, which will become negative, so negative 3/4 x squared plus 2x minus 1 dx. This is a pretty straightforward polynomial. It's just a definite integral of a quadratic. So I'll jump straight down to the answer. This one comes out to 0. Okay. So yeah, there's some work, but I mean, it's as far as double integrals go, it's a relatively painless one. And again, the idea that Green's theorem gives us, or that allows us, the tool that allows us to use, is to convert this line integral into a double integral, which in this case turned out to be easier to evaluate than the line integral would have been. It would have taken a lot more work and a lot more paper if we wanted to do this line integral directly. Okay, so that's going to be it for this first example, and we're going to keep expanding on Green's theorem, looking for more applications of it, but that'll be it for this first video.